All right, class. Hello. Today we're going to be talking about polygons. You already know something about polygons, but I'm going to go over some more definitions so that we have a clear understanding. Polygons are closed plane figures, which means that they're not going to be open like this. This is not a polygon. In order for it to be a polygon, you'd have to close it off. So now this is a polygon. And it also has to have 3 or more line segments called sides. So 3 or more sides. And we all know that the smallest polygon is a triangle because it has the smallest number of sides. Okay, and then the other requirements, so the first requirement, it has to be closed. It also has to have 3 or more sides. And the last requirement is each side intersects exactly 2 sides, one at each endpoint. So I know that may be a little bit confusing. So here's an example of a polygon where that case is true. Here's an example of something which is not true, because in this case this is not a polygon, because right here this side intersects 3 or more sides and intersects this side, and this side. So this would not be a polygon because for that very reason. So this is not a polygon. Instead of calling these line segments, which they are, we're going to call them sides. And instead of calling them corners, we call them vertices, or vertex for singular. There are 2 types of polygons, convex and concave. Now convex is ones that we normally deal with in everything that you've ever seen. A concave polygon is still a polygon, but the only difference is it's not convex. So I know that definition is confusing. So let me give you an example of a concave polygon, which according to the definitions, this is one of the most common concave polygons is a star. Because in this case, as you can see, it is closed. It does have straight line segments or sides, and each side intersects exactly 2 sides at the endpoints. But it's convex in that if I were to take a line and draw it from one end to the other end, I could actually be outside the polygon. So if it really is a polygon, then if I were to draw a line from one side to the other side, it will always remain inside the polygon. That's what makes this a polygon. But in this case, if I draw a line from this side to this side, I would actually have to go outside the polygon. So that's what makes this a convex polygon. I mean a concave polygon. This is concave, and everything else that you're used to seeing is convex. Okay? An n-gon is a polygon with n sides. So instead of saying a 12-sided polygon, instead of saying a dodecagon, we say 12-sided. Polygon is a 12-gon. So I know this is a lot of vocabulary, but you guys are familiar with it. We know what equilateral means. We know what equiangular means. What's very important is this new word called regular. And a polygon is regular if all the sides and angles are congruent. So basically a polygon is regular if it's both equilateral and equiangular. And we love those type of polygons. So those are the definitions. A diagonal is not a part of a polygon, but it is something that all polygons have, where you can draw, almost all, where you can draw a line segment from one vertex to another vertex, and it's going to be on the interior if it's a convex polygon. And so an example of a diagonal in this case would be something like this, because it's from one vertex, a line segment from one vertex to the other, as long as the vertices are not next to each other. So here's another diagonal. Okay, so that's the definitions. I want to talk about 2 very important properties that we're going to take a look at that's going to be very helpful. So let's take a look at the sum of the angle measurements of a polygon. We're going to start with a polygon with 3 sides, which we know is a triangle. What's the sum of all the interior angles of a particular triangle? We always know it's going to be 180 degrees. Okay. What about for a fourgon? Well, a fourgon is also called a quadrilateral, and we should also know that that is 360 degrees. So do we have a pattern where we could use that to predict the total sum of the interior angles of a five-gon, which is a pentagon? Well, what do you notice is the difference between 180 and 360? Well, some of you may figure out that's 180. So if I were to add 180 to 360, what number would I get? If you said 540, you were absolutely correct. But is that really the sum of the measure interior angle of a five-gon or a pentagon? Well, let's go to GeoGebra to figure that out. So here we have 4 pentagons, and as you can see, they each have angle measurements, and as I change them, it still says 540 until I make it a concave polygon. So for all convex pentagons, the sum of all the interior angle measures is always going to say 540. It changes when I change the pentagon or five-gon from a convex to a concave formula. Oops, sorry, that's the hexagon, sorry. So it's always 540 if it's a pentagon, and when I have a hexagon, which is over here, add another 180 and I get 720. So as I change this, you realize that it changes when it's no longer a convex polygon, but when I keep it a convex hexagon, the sum of the angle measurements is 720 for a hexagon. When I make it a septagon, which has 7 sides, again add 180 to 720 and you get 900, and I still keep it a septagon as 900 until I make it a concave polygon. Then it's no longer the case. But when it's a convex polygon, no matter how I change the angles, as long as it's convex and it's 7 sides, the sum is always 900 degrees. So that's our first relationship we want to look at. So is there a way to come up with a pattern to be able to communicate how many interior angle sum measurements of a polygon it has? Well, it is based off the number of sides, and as we increase the number of sides, the angle sum increases by 180 degrees. But it's not exactly the number of sides times 180 degrees, because if that's the case, 3 times 180 is not 180, so a triangle would not be 180. So we actually have to subtract 2 from the number of sides and multiply that times 180, and we'll get that information. So if a triangle has 3 sides, then 3 minus 2 times 180 is the angle sum. A quadrilateral has 4 sides. 4 minus 2 is 2 times 180 is 360, and vice versa. So we subtract 2 from the number of sides and multiply it times 180 to be able to get the total sum of the interior angles of a polygon. Now let's look at the exterior angles of a polygon. So here we have a 1, 2, 3, 4, 5, 6-sided polygon, a 6-gon or a hexagon. And I want to take a look at the exterior angles of the polygon. And the way, if I were to add all of these up, what would the answer be when I add them all up? Well, in this case, for those of you who have a calculator, if you add up all these values, you get 360. And the reason it is 360 is, I'm going to show you something. Let's see if I can show it to you. Is that, well, we'll talk about that in class because I want this video to be short. If I change the side of the polygons, if you notice, if I add these values up, I get 360. If I change the size and add them all up, this is where the 360 comes from. It's the fact that they all make a circle. So no matter how many sides a polygon has, the sum of the measures of the exterior angles is always going to be 360. So that leads to the last theorem on page 47, which is the sum of the measures of the exterior angles, whereas before we were talking about interior angles. In this case, the sum of the measures of the exterior angles of a convex polygon, it's still convex, is going to be always 360 degrees. Okay, so the sum is always going to be 360 degrees. And that's the end of this video. Sorry, I was a little bit longer than I wanted to be.